Swayam Prabha. Digital India. Educated India.
So, in the last class, we kind of briefly introduced what convex sets, convex functions are, and what is one specific implication of working with convex functions, something that we iterated upon multiple times. So, every local minima is also a global minima, right? So, with convex functions, so every local minima is also a global minima. But just the function being convex alone, it does not sort of eliminate the fact that you can have you can still have multiple optimizers, right? So, let us say I have a function which looks like this. So, every point here is a minimizer of this function. So, I can still have multiple minimizers, but all of them are going to be globally optimal. So, is there a class of functions where we are guaranteed, for instance, we are guaranteed to have just one unique minimizer? And the answer is yes. So, if the minimizer exists, so today we are going to look at something called strictly convex functions and strongly convex functions. So, for convex functions, what did we have? That if I evaluate, so this is f of lambda x plus 1 minus lambda y. For convex functions, what should this look like? So, less than or equal to lambda of f of x plus 1 minus lambda times f of y, right? And this is true for convex functions. So, this inequality which is less than or equal to, it does not eliminate the fact that you can have multiple local minimizers, all of them which are also going to be global minimizers, but you can still have multiple optimal solutions, right? With strictly convex function, as the term suggests, it is strict, right? So, that means this inequality is also going to be strict. So, for strictly convex functions, we have f of lambda x plus 1 minus lambda y. This is strictly less than lambda of f of x plus 1 minus lambda of f of y. This is true for every lambda in open interval 0 to 1 and x not equal to y. And this is the definition of strictly convex function or strict convexity. Okay. So, what does this strict inequality ensure? This ensures that every time you change a point, so one of the things that we notice with convex functions is, at least geometrically, what is happening is, suppose you have a function which looks something like this. So, for any points x and y, we know that the function value, so function like a convex combination of it, it's always below or at least not more than the convex combination of the function values f of x and f of y, right? But because of this less than or equal to, this may still be equal, right? And that is when you have these flat regions in your functions. With this strict inequality, we are guaranteed that this is going to be strictly smaller. So, this difference is going to be non-zero, right? And that is why strictly, with strictly convex functions, and if you have this difference to be non-zero, one of the things that you can clearly notice from this picture is, or this plot is, that it is guaranteed to have a unique minimizer, because every time as you move, you are going to be changing the function value. So, you are always going to be evaluating something which is going to be smaller than the convex combination of f of x and f of y. And one of the implications of strict convexity is, if the minimizer exists, it is unique, right? So this is the implication of working with strictly convex functions. Okay, all right. So how do we identify if a particular function is strictly convex? So a sufficient condition one way is to basically validate this particular definition of strict convexity, but like with convex functions, we had a second order condition for convexity, right, where the Hessian is positive semi-definite. So can we have an equivalent sort of condition? So sufficient condition for strict convexity is, so let's assume f is twice differentiable. Okay, and Hessian of f is positive definite. Okay, not positive semi-definite, but positive definite. Then f is strictly convex. So this is to say, like in the scalar case, that means f double prime is greater than 0. Then you have for every x, then you have f to be strictly convex. Okay. So what about, let's say if I look at a function like x to the 4, what is the Hessian of x to the 4? So Hessian of f is, so this is, let's say, f of x. Let me, so let's say if I choose, first of all, is this strictly convex? Is x to the 4 strictly convex? Does it have a unique minimizer? Right? So f x to the 4, this is strictly convex. Okay. What about the Hessian of f, this particular function? 12x square. Is this greater than 0? Is this? Not always, right? So this is greater than equal to 0, not strictly greater than 0, and that's why we call it a sufficient condition. So if this condition holds, then you are guaranteed that the function is going to be strictly convex. But if the condition does not hold, then you cannot guarantee otherwise that it's not going to be not going to be strictly convex, right? So it's a sufficient condition, not a necessary condition. Okay, but x to the 4, it's strictly convex because it almost looks like this, where you have a unique minimizer here. Is this clear? What about function like x square? Is this strictly convex? Right? Function is strictly convex, and what about the Hessian of this function? 2, which is strictly greater than 0. So this is, we can, using the second order condition, we can quickly validate that this function is strictly convex. So both these functions are strictly convex, but because this is a sufficient condition, we can only sort of implicate one way. So if the Hessian of f is positive definite, then function is going to be strictly convex, but the other way around need not be true. Okay. Is every strictly convex function a convex function? Right? Just by definition, every strictly convex function is also a convex function. So a strict convexity implies convexity. Other way around need not be true, right? If a function is convex, it need not be strictly convex. So for instance, a function which looks something like this is a convex function, but not a strictly convex function. Or a constant function, is not a strictly convex function, it's just a convex function. And similarly, the sufficient condition, so Hessian of f for every x, this implies strict convexity. So the reverse implication need not be true. Okay, but why do we care about strict convexity? So what's happening with convex functions? Like if I look at simple we have multiple minima, which is fine. I mean, because every minima is also a global minima. But you can see that something that happens with these kind of functions is that the gradients start vanishing, right? For this to happen, you have very small gradients around this particular value, right? And the gradients start vanishing. And think of it from the point of view of designing an optimization algorithm where you're using the gradient information. So if you're updating your x based on the past x and the current, like some step size and the current gradient value, so you are making smaller and smaller steps towards your optimal solution, right? Whereas from the point of view of strictly convex function, I mean, you don't really have that kind of condition where, I mean, you may still have larger gradient values around the optimal solution and you can converge to the optimal solution faster. So studying these class of functions has its own significance. The other thing is, if Hessian of f turns out to be positive definite, I mean, it need not be the case for all strictly convex function, but let's say for a particular strictly convex function, Hessian of f is positive definite, then that means you can also invert that Hessian, right? That is also invertible, and Hessian inverse is something, as we are going to look at it later, we can use Newton type methods to get even faster convergence. So when Hessians are going to be invertible, so strictly convex functions in that sense have a significant role to play. So in some sense, convex functions are more general. Strict convexity in some sense is a sort of stronger assumption on the function. There's even more like stronger assumption which is called strongly convex function or strong convexity. So let's look at it. Okay, what is so far for a simple convex function, we know that f of lambda x plus 1 minus lambda y, this is less than or equal to lambda times f of x. So this is for a convex function. For a strictly convex function, this basically holds with strict inequality. As long as lambda is between 0 and 1 and x and y are different points, this becomes strictly convex function. So what you are saying is that the function value, so the function evaluates to a smaller value than the convex combination of the function values, but it does not tell you by how much. So in a strongly convex function, you also provide values. So strongly convex would look something like this. So first of all, this function is going to, so this is your convexity part. Additionally, you can guarantee that, so in convexity, you have this right hand side, right? So this particular right hand side is going to exceed the left hand side at least by this much amount. Okay, so there exists some mu greater than 0, and this mu is called modulus of strong convexity. So for strictly convex function, we say that the right hand side exceeds the left hand side. For strongly convex function, we also provide the amount by which the right hand side exceeds the left hand side. So we say that basically it exceeds by this much amount. Okay. So that is a sort of more restrictive assumption on the kind of function that you can have, where you also say that no matter what your x and y are, there exists some mu greater than 0 such that the right hand side is going to exceed the left hand side by this much amount. And as y is very close to x, let's say y is equal to x, then this quantity is anyway 0. But then as y is close to x, I mean basically the amount by which it exceeds is going to get smaller. But you specify a rate by which like the right hand side exceeds the left hand side. So that means when you are doing gradient descent, you will always have some definitive rate coming from this additional term. Whereas that may not be the case with your convex function or even strictly convex function, right? So one of the things that we saw at the beginning of this particular course is optimizing x to the 4 versus optimizing x square, right? With x square, so x square basically is strongly convex function. It's not just strictly convex; it's also strongly convex. Okay. So whereas x to the 4 is just strictly convex. So we know that closer to the optimal solution with x to the 4, it sort of varies slowly. Whereas x to x square, it still has a definitive gradient, and therefore those kind of functions you can optimize much faster, and that's why it's called strongly convex function. Strongly because you're making stronger assumptions on the convexity of the function. Okay, so in terms of implication, we have strong convexity, which implies strict convexity, which implies convexity. Okay, so this is how the implication goes. Is this clear? So an example would be x square. So a second order necessary and sufficient condition for strongly convex functions is, so assume that f is twice differentiable. Then let me write it this way. F is mu strongly convex. So from now on, I'm going to denote strong convexity with SC. Okay. So f is mu strongly convex if and only if Hessian of f looks something like this. Huh? Yeah, twice continuously differentiable. You can, in this case, you probably don't need the continuity as long as it's twice differentiable, but that's fine. Usually with first order definition, you need the continuity because you write f of y in terms of f of x in. But yeah, so this is if and only if kind of condition, that f is mu strongly convex if and only if Hessian of f is not just positive definite, but it's basically lower bounded by this. So you can see the model of strong convexity also appearing in over here. Okay. So if f of x is x square, what is mu in this case? 2, right? So f of x is strongly convex with mu equal to 2. Yeah.
Strongly convexity would mean that at every step there would be some gradient gap.
Right. So
how are we, the main question, how are we concluding that strongly convexity will imply strict convexity?
Because if you look at this condition, right? So that means Hessian of f is strictly greater than 0 because it's lower bounded by mu greater than 0, right? So then if I use this second order sufficient condition, then it's okay. No, this is if and only if. Okay. So we had the first order condition for convexity, and so just to briefly recall. So what was the first order condition for convexity? F of y is greater than or equal to f of x transpose y minus x, right? And pictorially speaking, what did that imply? Suppose you have a function which looks something like this, and if I compute a gradient at one particular point, let's call it x, and this is another point y, take this point as y, so this is f of y. So essentially the function, in some sense the function would have moved upwards. If I keep moving in the direction of the gradient, the function would have moved upwards, right? So this is what this particular condition captures. In case of strong convexity, so we have an equivalent definition of first order characterization of a strongly convex function. So first order condition for a strong convexity okay. So here we say that the function not only moves upward, but it moves by this much amount, at least by this much amount. So this gap is going to be at least this much. right? So, in some sense you are trying to sort of impose a condition on the gradients, that the gradients are not going to be like vanishingly small, right? Because you are, all the time you are specifying that you are going to be moving upwards by at least this much. Is this clear? So, this is pretty much the gap, and it says that, like for instance, if this particular first order condition holds with equality, so that means the function is moving, like if I move in the direction of the tangent, the function is pretty much moving along that line, right? Whereas here, I mean, the function is moving upwards, so we are getting larger and larger gradients every time, and not only it moves upwards, but it moves upwards at least by this much amount. And this basically helps when we are closer to the optimal solution. So, we know that there is always going to be gradient because of this particular condition, like non-vanishing kind of gradient because of this condition. Okay. So, all these definitions are the first order condition for convexity. I mean, so these make sense when f is continuously differentiable, let us say, right. But what if f is not differentiable? What do we do? So, if the gradient of f does not exist, can we still use these first order conditions for convexity or strong convexity? The answer is yes. And so, let me just make a quick remark. So, when f is not differentiable, so then gradient of f need not exist, right. So, we use something called subgradients. So, we'll look at this subgradient part later in the course, but just to tell you what subgradients are. So, consider a function which looks, so basically f of x is equal to mod x, right. So, what is the gradient for any x greater than 0? 1, right. For x less than 0, the gradient is negative 1. And what is the gradient at x equal to 0? Not defined, right. But when we can define something called subgradient would be any line such that it sort of is below the curve, right. So, again, one of the definitions of convexity is if we move along that particular line, the function would have moved upwards, right. So, subgradient for this function is defined to be plus 1 if x is greater than 0, minus 1 if x is less than 0, and any number if x is equal to 0. And we can write down the equivalent definition as fy is greater than or equal to f of x plus g transpose y minus x. Instead of using the gradient of f of x transpose y minus x, we can define the equivalent, like we can write down the equivalent sort of characterization of convexity in terms of something in terms of subgradients. And just to verify this for x equal to 0, so for x equal to 0, fy is greater than or equal to f0 is simply 0, g transpose y, right. In this case, g is just a scalar, and as long as y, let us say y is positive, and if I choose g to be between minus 1 and 1, then we know that this function sort of exceeds for positive y and so on, right. So, this constraint is satisfied for example, for this particular choice of subgradient. So, whenever gradients are not defined, we write down the equivalent characterization because the function is convex. So, it must follow some kind of first order convexity condition, and when gradient is not defined, we basically define it using subgradients. And we can use the same subgradient, even like same subgradient definition even for strongly convex functions. Is this clear? Any questions so far? Yeah. Yeah, x to the 4, right. So, the question is there a function which is strictly convex but not strongly convex, and that is x to the 4. If you take the Hessian of x to the 4, that's 12x square, and you cannot lower bound it by some mu, right, like, because it will vary with x. So, yeah, whenever I say strongly convex, the picture that you should have in your mind is something like x square, something equivalent of x square. I mean, there are other functions which are also strongly convex, but x square is the most commonly sort of used strongly convex function. Something which is strongly convex, something which is strictly convex but not strongly convex would be x to the 4, and anything which is like, I mean, I mean, next all these functions are anyway going to be convex, right? So, all right. So, we are going to look at a few implications of strong convexity and how they sort of. So, one of the things that strongly convex functions satisfy is by the way, do strongly convex functions have unique minimizer? Yes, right? Because strongly convex functions are by definition also strictly convex, and strictly convex functions have unique minimizers, so they would also have unique minimizers. So, strongly convex functions satisfy something called PL inequality. So, PL stands for Polyak-Loesch's inequality. So, this condition is also called gradient dominance condition. And this PL inequality is given by, so PL inequality is where f star is the optimal value of the function. In some sense, what this definition is trying to say is that function at least has a quadratic growth, quadratic type of growth. And the reason why PL inequality is particularly important is, now if you remember that in the first lecture, we looked at a function of the form. So, we know that f of x equal to half x square or x square, this is strongly convex, right? And you can verify this definition is, I mean, trivially satisfied, right? So, gradient of f of x is 2x, right? So, that will be 4x square divided by 2. So, 2x square is going to dominate, and in this case mu is also 2. So, I mean, in fact, this is satisfied with kind of equality, but there is a class. So, if I look at a function of this form, g of x is x square plus 3 sine square x, the plot of this function looks something like this. Something like this. So, is this strongly convex? Is this function strongly convex? It is not even convex, right? I can draw a line and the function sort of evaluates to a value which is more than the convex combination of the function, like evaluations at these points, right? So, this function is not even convex to start with, forget about it being strongly convex. But this function still satisfies this PL inequality, right? And so, in terms of hierarchy, so we know that the implication goes this way, right? So, strongly convex functions, strong convexity implies strict convexity implies convexity. So, you have a larger sort of, let us say this is all convex functions. Within this class, you have functions that satisfy, let us say, which are strictly convex. Then within this class, we have functions which are strongly convex. And not within this class entirely, but you have another class of functions which satisfy PL inequality, which also includes strongly convex function, but so these are the functions that satisfy PL inequality. Okay. So, this is not a convex function, but it still has a unique minimizer, right. So, this, for instance, this particular function is very different from a function which looks something like this, which is which we know that has multiple local minima. In this case, you still have a unique minimizer. So, near the optimal solution, it behaves like a strongly convex function, but far from the optimal solution, it doesn't behave like an strongly convex function. So this function, these kind of functions are called invex functions.
So all the strongly convex functions
By the Peer inequality, yeah.
that would be a subset strongly.
No, but then there are functions which are not even strongly convex but also satisfy Peer inequality, right?
But the strongly convex should be a subset of those functions that satisfy P.
Yeah, yeah, you can extend it this way. Thanks for pointing this out. Yeah. Okay. All right. So we are going to look at few implications of strong convexity, and yeah.
Every function which sort of has a parabolic shape in some local minimum will be an invex function, right?
Invex function, yes. I mean, but then you can generalize this more, and you can say it's going to be even like, I mean, it's also going to be convex. In this case, I mean, it's not convex, right?
Yeah.
So invex functions, I mean, they have their own, like, I mean, there is a particular definition for mathematical definition for invex function. What I just wanted to, I mean, without getting into the details, what I just wanted you to look at is, so this function is not even convex.
Yeah.
And in more often than not, you will come across functions. So for instance, when you so something like, for instance, so this function is strongly convex, right? But then if I do an affine transformation of this, you can show that this is not strongly convex for any A. So only when A is full row rank, then this function is strongly convex. But you can show that this function still satisfies the Peer inequality. So by studying the class of functions which satisfy Peer inequality, you are, I mean, and if you can guarantee, let's say you're designing an optimization algorithm and you say my optimization algorithm works for functions that satisfy Peer inequality. So by being able to do so, you know for sure that if your optimization algorithm works for strongly functions that satisfy Peer inequality, it will work by definition for functions that satisfy strongly that are strongly convex, but that are also potentially not convex, something like this. So this function is not convex to start with, but you can still guarantee convergence to the optimal solution for this class of functions. So, and we are in this course, we are going to design algorithms and guarantee that those algorithms would converge faster for functions that satisfy Peer inequality alone, without those functions even being convex to start with.